Today is August 17th, 2026. This is an AI-generated research overview and requires human review before its claims are reused. The source collection is partial, although it contains analyses of 32 papers and several underlying records were incomplete. The clearest theme is evaluation. Researchers are asking not merely whether an AI system succeeds, but how it behaves, where it fails, whether its evidence is sound, and whether performance survives realistic deployment shifts.
That shift is especially visible in long-horizon research agents. One study evaluated 7 frontier models across 36 executable research and engineering tasks, with 3 attempts per task. Its leading system averaged 0.739 and reached 0.790 when taking the best of 3 attempts. More importantly, similar final scores concealed different weaknesses in framing, execution, and feedback use. A related discovery benchmark found process scores moderately associated with outcomes, but its reported repair gains lacked an unguided rerun control, so ordinary run-to-run variation remains a plausible explanation.
Robotics evaluation tells the same story from a different angle. Endpoint success can hide unstable movement, poor recovery, or physically implausible execution. A humanoid motion benchmark reported that its learned trajectory score agreed with strict expert preferences about 91% of the time, above every individual analytic metric tested. Another toolkit inferred progress, regression, and recovery from robot video. Its best process model reached 0.77 macro F1 overall, yet detected rising progress much better than falling progress. These are measured results, not proof that either metric captures human judgment universally.
Reliability under deployment shift produced the most alarming numbers. In a crisis video benchmark, traditional detector performance was weak across unfamiliar generators. After a controlled bundle of social media-like transformations, mean area under the curve fell from 51.4 to 47.3%. Across 5 fine-tuned configurations, fake video recall collapsed from 46% to 1.4%, largely because systems shifted toward calling videos real. The benchmark is visual only and uses predefined transformations, so it does not measure full real-world misinformation chains involving audio, captions, repeated reposting, or social context.
A separate multimodal safeguard offers a more encouraging but narrower result. A token-level hallucination detector used internal model representations to decide when caption tokens should be resampled. On one image caption benchmark, 2 hallucination measures fell from 18 and 37.2 to 8.2 and 16.6, at about 6% additional latency. That is direct benchmark evidence. The important constraint is operational. The method needs internal access and separate training for each backbone, so it is not automatically portable to closed models or unseen architectures.
On-policy learning appeared in several forms. Visual self-distillation gave a student a degraded image, while an exponential moving average teacher saw the clean image. A 4 billion parameter model's average across 6 perception benchmarks rose from 70.68 to 77.44%. Another method transferred mathematical reasoning across incompatible tokenizers by supervising only exactly aligned text spans. Its largest highlighted proof score rose from 21.7 to 44.5, but the value depended on the judging model. Unmatched spans were discarded, and neither study established generality beyond its tested model families.
A third distillation study compressed successful prior trajectories into latent context used only during training. For a 4 billion parameter agent, environment reward increased from 0.486 to 0.637, and the deployed student no longer needed retrieval. Yet, more latent capacity was not consistently better. No multi-seed uncertainty was reported, and total training cost was omitted. Another paper warns why that matters. Sequential optimization improved one instruction following score while reducing the diversity of answers that could earn future reward. Immediate gains may therefore shrink what later training can recover.
Several papers replaced opaque pixel prediction with explicit structure. One game world model predicted articulated state, rendered geometry deterministically, and then painted appearance with diffusion. A terrain correction reduced collision frames from 0.337 to 0.114, and penetration from 0.444 to 0.157 meters. Those corrections directly target measurable physical failures, but evaluation covered one monster and task regime, with only 12 rendered rollouts for its video metric. A related spatial model generated geometry, flow, poses, and answers natively, though missing table cells and relative scale outputs limit interpretation.
Evidence grounding also moved below document-level relevance. A parliamentary retrieval system inserted exact quotations and achieved perfect quotation faithfulness over 15 topics, compared with 0.95 for a reference system. However, none of its corrected human evaluation differences was statistically significant. A legal benchmark asked whether the cited page actually supported a proposition. Recall on deliberately wrong pages ranged from roughly 37 to 83%, depending on dataset and configuration. Together, these results support an editorial conclusion. Retrieving something topical is weaker than verifying the precise claim. They do not imply either paper influenced the other.
Internal feature studies followed a similarly causal direction. One language model study found that ablating neurons associated with the same task domain reduced accuracy by 25.9% versus 2.5% for cross-domain ablation. A multimodal study removed selected features and reduced a spatial reasoning score by 10 to 15 points, while changing a general visual question score by at most 1.5. These interventions strengthen the case that the selected features matter behaviorally. Still, restricted architectures, predefined domains, chosen datasets, and narrow intervention protocols do not establish uniquely identifiable cognitive modules.
Efficiency claims require careful separation. One optimizer reported up to 6.5 times lower optimizer step time in a particular accelerator setup, not 6.5 times faster end-to-end training. Chunked prefilling on one Apple Silicon machine increased the demonstrated prompt length from 4,096 to 11,231 tokens, while slowing shorter prompts. Parallel background reasoning reduced median software task time from about 257 to 229 seconds, but raised application programming interface cost by roughly 66 to 182%. The settings differ, so these numbers should not be ranked directly.
The takeaway is that better AI research increasingly depends on measuring hidden failure modes: process quality, support preservation, causal shortcut reliance, proposition-level evidence, physical state, and deployment robustness. The strongest next experiments are controlled ones. Compare repaired agents with unguided reruns, validate robot process metrics with independent humans and real hardware, test video defenses through combined audio, caption, compression, and reposting shifts, and report end-to-end cost on matched systems. Because this daily run is partial and some source records were truncated, treat the numbers as bounded evidence, not a complete field survey. For paper-level details and links, consult the linked daily summary.